In the shadows of classified military research facilities, beyond the reach of public knowledge, America's defense scientists are quietly developing something that will change warfare forever. While the world focuses on the F-47 and other sixth-generation aircraft, a secret project with unprecedented capabilities is taking shape, one that could dominate the skies and space for decades to come. Today, we reveal what military insiders have been whispering about: America's secret seventh-generation fighter jet. What you're about to learn has been kept from public view, hidden behind layers of military classification. This isn't science fiction. It's the future of aerial dominance being developed right now, a machine so advanced it makes current stealth technology look primitive by comparison. The Pentagon doesn't want you to know about this program. Defense contractors won't acknowledge its existence. Foreign intelligence agencies are desperately trying to uncover its details. Yet through careful analysis of defense budgets, technical publications, and insider accounts, we've pieced together the story of America's most ambitious military aviation project ever. Support this by sharing your thoughts in the comments about what capabilities you think are most important for America's next advanced fighter jet. Beyond the F-47, the next leap forward. The recent announcement of the F-47 fighter jet marked a milestone in military aviation. As President Trump proudly declared, nothing in the world comes close to it.
Nothing in the world comes even close to it.
The F-47, classified as a sixth-generation fighter, represents the pinnacle of current, publicly acknowledged military aviation technology. But within the corridors of the Pentagon and the secret facilities of defense contractors, attention has already shifted to something far more revolutionary. Defense Secretary Pete Hegseth recently hinted at technologies beyond current imagination during a closed congressional hearing. While he didn't explicitly mention a seventh-generation fighter, his comments align with reports from military analysts about shifting research priorities. The reality is this: America never stops innovating when it comes to defense. The moment one generation of technology is deployed, work on its replacement begins. The seventh-generation fighter concept represents a fundamental rethinking of what an aircraft can be. Unlike the incremental improvements between fourth and fifth-generation fighters, the leap from sixth to seventh will be transformative. This isn't merely speculation. A careful analysis of defense appropriations reveals significant funding increases for advanced aerospace concepts within DARPA and Air Force Research Laboratory budgets. These allocations, often buried in technical line items, show a clear pattern of investment in technologies that go beyond anything incorporated in the F-47 program. Furthermore, recent patent filings from major defense contractors contain descriptions of propulsion systems, materials, and control mechanisms that would be unnecessary for current-generation aircraft. These patents, while deliberately vague in their applications, provide a technological roadmap pointing directly toward capabilities only a seventh-generation platform would require. Perhaps most telling is the recent construction of new testing facilities at Edwards Air Force Base and other locations. These highly secure complexes feature specialized equipment for evaluating aerospace systems under conditions that simulate both hypersonic atmospheric flight and exoatmospheric operations, exactly the capabilities a seventh-generation fighter would need to demonstrate. What makes a fighter seventh generation? The answer lies in several breakthrough technologies being developed simultaneously. First, true hypersonic capability. While current aircraft can reach hypersonic speeds for brief periods, the seventh-generation platform would maintain speeds above Mach 5 as its standard cruising velocity. This isn't just about going faster, it's about completely changing the tactical equation. At such speeds, the aircraft could strike anywhere on Earth within hours, making it virtually impossible for adversaries to prepare. DARPA's Advanced Aircraft Infrastructure-Less Launch and Recovery Program, known as ANCILLARY, provides clues about this development. While officially focused on drone technology, the program's innovations in vertical takeoff and landing could be applied to this next-generation manned fighter. The propulsion system enabling this performance represents a quantum leap beyond conventional jet engines. Defense industry sources describe a combined cycle propulsion system that integrates multiple engine types, turbofan, ramjet, scramjet, and possibly even more exotic technologies. This would allow efficient operation from standstill through hypersonic regimes, addressing the primary limitation of current high-speed aircraft. The second breakthrough involves space operations. Unlike any previous fighter, the seventh-generation aircraft would be capable of exiting and re-entering Earth's atmosphere. This isn't just about achieving altitude, it's about creating a true aerospace vehicle that can engage threats in multiple domains. This capability would allow it to conduct anti-satellite operations, intercept ballistic missiles in their mid-course phase, and provide unprecedented surveillance capabilities. Imagine an aircraft that could orbit Earth like a satellite, then descend into the atmosphere to strike with precision. Engineers at NASA's Armstrong Flight Research Center have reportedly been consulting on thermal protection systems derived from spacecraft technology. These advanced materials would protect the aircraft during the intense heat of atmospheric re-entry, solving one of the most challenging aspects of aerospace vehicle design. The third revolutionary aspect is advanced artificial intelligence integration. Beyond the autonomous systems of sixth-generation fighters, the seventh-generation platform would employ generative AI capable of adapting to previously unencountered situations. This isn't just automation, it's true machine cognition applied to warfare. This AI wouldn't just assist human pilots, it would function as a full partner, capable of independent decision-making when communications are compromised. In unmanned configurations, multiple aircraft could operate as a networked swarm with distributed intelligence. The computational architecture supporting this AI represents a departure from traditional systems. Rather than relying solely on conventional processors, the system would incorporate neuromorphic computing elements that mimic the structure and function of the human brain. This approach enables pattern recognition, decision-making, and adaptation capabilities far beyond current systems, while consuming significantly less power. Defense officials speaking on condition of anonymity indicate that current AI test programs have already demonstrated the ability to outperform human pilots in simulated combat scenarios while adapting to novel threats never encountered during training. These programs, while impressive, represent merely the foundation for the far more sophisticated systems planned for the seventh-generation platform. For decades, stealth technology has focused on reducing radar cross-section through shape and materials. The seventh-generation fighter represents a fundamental reimagining of what stealth means. Rather than simply avoiding detection, this aircraft would employ active countermeasures that make it effectively invisible to all sensing systems. This includes advanced electromagnetic manipulation that can bend radar waves around the aircraft, quantum sensing disruption, and adaptive camouflage that responds to surrounding conditions. The most revolutionary of these technologies is plasma stealth, the ability to generate an ionized field around the aircraft that absorbs or disrupts incoming radar waves. While theoretical papers on this technology have circulated for decades, practical implementation has remained elusive until recently. Advanced power management systems now make it possible to generate and control such fields with unprecedented precision. Military technology analysts point to unusual radio frequency tests conducted at remote facilities in Nevada and Alaska as potential evidence of plasma stealth development. These tests, detected by amateur radio operators, exhibited signal characteristics consistent with the electromagnetic disruption plasma stealth would create. The aircraft's flying wing design, similar to the B-21 Raider but more advanced, would give it a radar cross-section smaller than a bird. Combined with heat-masking technology that makes infrared detection impossible, the aircraft would be virtually undetectable by conventional means. Thermal signature management represents another quantum leap. Current aircraft attempt to hide their heat signature through exhaust cooling and careful design. The seventh-generation fighter would take a different approach, employing dynamic thermal redistribution systems that spread heat across the entire airframe until it matches the surrounding environment almost perfectly. This technology draws from principles being explored in advanced submarine acoustic signature management. Defense industry sources report that the platform would also incorporate revolutionary materials developed through 4D printing, an advancement beyond current 3D printing that allows materials to transform their properties in response to environmental conditions. These materials would be self-healing, capable of repairing damage during flight, and could alter their radar-absorbing properties as needed. The structure would be lighter yet stronger than anything currently flying, allowing for unprecedented performance while maintaining stealth characteristics. The extreme secrecy surrounding these metamaterials makes details scarce, but academic research provides glimpses of what might be possible. Materials that can change density, electrical conductivity, and even optical properties in response to electrical signals or environmental conditions would provide unprecedented adaptability. An aircraft covered in such materials could optimize itself for different mission phases, maximizing stealth during penetration, heat dissipation during high-speed flight, and structural rigidity during combat maneuvers. Patent filings from major defense contractors and specialized materials companies reveal steady progress in developing these technologies, with some described as reaching technology readiness levels suitable for integration into advanced aerospace platforms. The seventh-generation fighter wouldn't just fly differently, it would fight differently. Its weapon systems would represent as significant a leap forward as the platform itself. Directed energy weapons, military-grade lasers, would form the primary armament. Unlike experimental systems currently being tested, these weapons would be powerful enough to destroy aircraft, incoming missiles, and even targets on the ground instantly. The technical challenges of airborne laser weapons are formidable. Power generation, thermal management, atmospheric interference, and beam control have all limited previous attempts. However, recent breakthroughs in solid-state laser technology, compact power systems, and adaptive optics are changing the equation. The Missile Defense Agency and Air Force Research Laboratory have made significant progress in these areas, with test systems demonstrating unprecedented power and accuracy. A defense industry executive with knowledge of these programs recently stated that directed energy weapons have crossed the threshold from experimental to operational, suggesting that deployment on advanced platforms is now feasible. The energy output would be managed through revolutionary power systems that generate more electricity than any current aircraft. This power generation would support not just weapons, but also advanced electronic warfare capabilities that could disable enemy systems without firing a shot. These power systems likely combine multiple technologies: advanced thermal generators exploiting the extreme temperature differentials in hypersonic flight, quantum photovoltaic systems that harvest energy across a broader spectrum than conventional solar cells, and possibly even more exotic power sources that remain strictly classified. For kinetic operations, the fighter would carry hypersonic missiles capable of striking targets at ranges previously unimaginable for tactical aircraft. These missiles would themselves be stealth platforms, making defense against them nearly impossible. Unlike current hypersonic weapons, which trade maneuverability for speed, these next-generation missiles would maintain extreme maneuverability throughout their flight profile. This capability, achieved through advanced control surfaces and thrust vectoring, would make them virtually impossible to intercept, even if detected. Patent filings suggest these missiles might incorporate multi-mode propulsion systems that allow them to adapt to different flight regimes, potentially even transitioning between air-breathing and rocket propulsion as needed. This approach would combine the efficiency of air-breathing engines with the performance of rockets, maximizing both range and terminal effectiveness. The aircraft would also deploy autonomous drone swarms as force multipliers. These drones, linked to the main platform through quantum communication networks immune to jamming, would extend the fighter's sensor range and striking power exponentially. Military analysts believe these drones would be far more sophisticated than current autonomous systems. Rather than simply executing pre-programmed missions, they would function as an extension of the main platform's capabilities, adapting to changing battlefield conditions and coordinating their actions without human intervention. Perhaps most revolutionary would be the aircraft's potential space-based weapons capabilities. With its ability to operate beyond Earth's atmosphere, it could deploy anti-satellite weapons with unprecedented precision, potentially changing the balance of power in space. These capabilities might include directed energy systems optimized for the space environment, kinetic kill vehicles designed to intercept satellites or ballistic missiles in their mid-course phase, and possibly even systems designed to disable rather than destroy targets through electronic or cyber means. A former Space Force official recently commented that space is no longer a sanctuary. and that capabilities to defend American assets in orbit are advancing significantly, potentially alluding to these developing systems. Despite its revolutionary technology, the seventh-generation fighter raises profound questions about the future role of human pilots. Military planners face a crucial decision. Should such an advanced platform be manned, unmanned, or optionally manned? The challenges of human operation at hypersonic speeds and space altitudes are formidable. The physical stresses would exceed the tolerance of even the most highly trained pilots without significant advances in life support systems. Medical researchers at the Air Force Research Laboratory have been studying these challenges for years. Their work includes advanced pressure suits that automatically compensate for extreme G-forces, neurological interfaces that help the human brain process information at superhuman speeds, and even biological enhancements that could increase human tolerance for extreme conditions. A former test pilot involved in these programs described the experience as redefining what it means to be a pilot. Rather than simply operating controls, pilots would enter a state of enhanced integration with their aircraft, processing sensory data, and making decisions at speeds impossible with conventional interfaces. Yet fully autonomous operation raises its own concerns about command and control in complex combat environments. The solution likely lies in a hybrid approach. Pilots operating from remote locations, using neural interfaces that provide sensory feedback indistinguishable from being physically present in the aircraft. This embodied telepresence would allow human decision-making while removing physical limitations. The fighter could operate unmanned for extended missions, with human pilots jumping in virtually when needed for critical decisions. The technology enabling this approach draws from multiple disciplines: virtual reality, neural interface research, quantum communication, and artificial intelligence. While each component exists in some form today, their integration into a seamless system represents a significant challenge. DARPA's Neural Engineering System Design program provides hints at the direction this technology is taking. Originally focused on restoring sensory capabilities to disabled individuals, the program has demonstrated the ability to create direct, high-bandwidth connections between human brains and external systems. Military applications represent a natural extension of this research. A senior military official recently commented that the distinction between manned and unmanned systems is becoming increasingly meaningless, suggesting that this hybrid approach is gaining traction within defense planning circles. Military experts believe this approach represents the future of combat aviation, combining the adaptability of human intelligence with the physical capabilities of machines, unconstrained by human limitations. This human-machine integration extends beyond just operation of the aircraft. The training of pilots for these systems would itself represent a revolution, combining physical training with neural interface conditioning and even cognitive enhancement techniques designed to maximize human performance within this new paradigm. The ethical and operational implications are profound. What does it mean when a pilot can control multiple aircraft simultaneously? How does the risk calculation change when the pilot's physical body is no longer at risk? These questions are actively being debated within military and defense policy circles, even as the technology rapidly advances. Why is America pursuing such an ambitious project? The answer lies in emerging threats that could challenge current air superiority assumptions. China's rapid military modernization includes its own next-generation fighter programs. The White Emperor project, while officially classified as sixth generation, reportedly incorporates technologies that overlap with seventh-generation concepts. Defense intelligence reports indicate that China's aerospace industry has made unexpected advances in several critical areas, including hypersonic propulsion, quantum radar systems, and advanced materials. Their integrated air defense systems are increasingly capable of threatening even stealth aircraft, potentially eroding a key American advantage. Chinese military publications have openly discussed aerospace integration as a core capability for future conflicts, suggesting their own ambitions extend beyond traditional air defense into the space domain. Satellite imagery has revealed expansion of test facilities in remote Western China that appear designed for testing advanced aerospace platforms. Similarly, Russia's PAK-DP program aims to leapfrog current fighter generations with revolutionary propulsion systems and weapons capabilities. While Russia's economic challenges have slowed development, the technological ambition remains. Russian aerospace firms have maintained expertise in several niche areas despite broader economic constraints. Their work on plasma stealth technology in particular has reportedly yielded significant results. Russian defense officials have made increasingly confident statements about their ability to detect and track stealth aircraft, claims that, if true, would represent a serious challenge to current American air dominance strategies. A senior Pentagon official recently testified before Congress that peer competitors are advancing their aerospace capabilities at rates that should concern us all, adding that maintaining technological superiority requires not just incremental improvements, but revolutionary leaps in capability. For America, maintaining absolute air superiority isn't optional, it's existential. The 7th-generation fighter program represents a determination to ensure that no adversary can ever achieve parity in the air domain. The emergence of sophisticated integrated air defense systems has already complicated mission planning for current stealth aircraft. As these systems continue to evolve, the need for platforms with fundamentally superior capabilities becomes increasingly urgent. The alternative, contested airspace where American forces cannot operate with impunity, would represent a strategic shift with profound implications for global security. A recent wargame conducted by a prominent defense think tank concluded that without significant advances in penetrating capability, American air power could face unprecedented challenges in potential conflict zones by the mid-2030s. This assessment has reportedly accelerated interest in revolutionary platforms rather than incremental improvements to existing systems. This strategic imperative has accelerated development timelines. While previous fighter generations took decades to mature, the 7th-generation program is reportedly compressing this timeline significantly through advanced simulation, artificial intelligence-assisted design, and revolutionized manufacturing. The traditional development cycle for fighter aircraft, concept, design, prototyping, testing, refinement, production, typically spans 20 to 25 years. By leveraging digital engineering, artificial intelligence-assisted design, and advanced simulation capabilities, defense officials believe this timeline can be compressed by as much as 50%, potentially bringing revolutionary capabilities to operational status within a decade. A senior Air Force acquisition official recently stated that the days of 20-year development cycles are behind us, adding that the threat environment simply doesn't allow for that luxury anymore. The 7th-generation fighter couldn't be built using traditional aerospace manufacturing methods. Its production represents a revolution in how military aircraft are constructed. Additive manufacturing, advanced 3D printing, forms the cornerstone of this approach. Rather than assembling components, the aircraft would be grown as a nearly seamless whole, eliminating weak points and reducing radar signature. This transition is already underway in the aerospace industry. Major defense contractors have invested billions in advanced manufacturing facilities that bear little resemblance to traditional aircraft production lines. These facilities feature massive 3D printing systems capable of producing structural components many meters in length with microscopic precision. A senior aerospace executive recently revealed that we're now printing components that couldn't be manufactured any other way, adding that these parts exhibit performance characteristics that were previously thought impossible. These components include structural elements with internally optimized geometries that would be impossible to machine or forge using conventional methods. This process would extend to what researchers call 4D printing, creating materials that can change their properties in response to environmental stimuli. These programmable materials would allow the aircraft to adapt its structure during flight for optimum performance. Research in this area is progressing rapidly. Academic papers describe materials that can change shape, density, and electrical properties in response to temperature, electric fields, or mechanical stress. Military applications of these technologies remain classified, but their potential for aerospace systems is profound. A materials scientist working in this field described the potential as breaking the paradigm that structures must be static. Instead, future aircraft could continuously optimize themselves for changing flight conditions, actively damping vibrations, managing thermal loads, and even altering their aerodynamic properties in real time. Quantum computing plays a crucial role in designing these complex systems. Problems that would take conventional supercomputers years to solve can be addressed in hours, allowing for unprecedented optimization of every aspect of the aircraft's design. Major defense contractors have established partnerships with quantum computing pioneers to explore these applications. While fully functional quantum computers of sufficient scale remain in development, even the current generation of quantum systems has demonstrated the ability to solve complex optimization problems relevant to aerospace design. The computational challenges are staggering. Designing an aircraft that can operate effectively from sea level to the edge of space, from subsonic to hypersonic speeds, requires modeling physical phenomena across multiple domains simultaneously. Traditional computational approaches simply cannot handle this complexity with sufficient fidelity. A computer scientist involved in these efforts described the quantum approach as not just faster, but fundamentally different, enabling design teams to explore solution spaces that would be inaccessible using conventional methods. The result would be an aircraft that doesn't just incorporate advanced technology, it would be built using methods that themselves represent technological breakthroughs. This manufacturing revolution extends beyond the aircraft itself to its support systems. Maintenance would be transformed by real-time structural health monitoring, predictive analytics, and on-demand manufacturing of replacement components. The concept of fixed maintenance schedules would be replaced by continuous assessment and adaptation, dramatically increasing availability while reducing lifecycle costs. When might we see this revolutionary aircraft in service? Defense analysts have pieced together a timeline based on budget allocations, research program schedules, and industry movements. The conceptual phase is already complete. Detailed design work is reportedly underway, with prototype subsystems being tested in classified facilities. The first technology demonstrator, not a full aircraft but a platform to validate key systems, could fly within 5 years. Evidence for this timeline comes from multiple sources. Analysis of defense budget documents shows significant increases in funding for advanced technology demonstration programs within both the Air Force and DARPA. While these programs are not explicitly identified as related to seventh-generation fighter development, their technical objectives align perfectly with the capabilities such an aircraft would require. Industry movements provide additional clues. Major aerospace companies have been quietly recruiting experts in hypersonic propulsion, advanced materials, and artificial intelligence at an accelerated pace. New secure facilities have been constructed at traditional aerospace research locations, with unusual security measures suggesting work on highly classified programs. A fully functional prototype might be operational by the mid-2030s, with initial operational capability possible by 2040. This timeline is ambitious but reflects the accelerated development approach being employed. This approach draws lessons from previous acquisition programs. The troubled development of the F-35, which faced significant delays and cost overruns, has informed a new philosophy that emphasizes thorough technology maturation before integration into complete systems. Rather than developing an entire aircraft and then discovering problems, each critical subsystem is validated independently before being incorporated into the overall design. The ambition of the seventh-generation fighter program comes with significant financial implications. While exact figures remain classified, defense budget analysts estimate development costs could exceed $100 billion over the next decade. This investment reflects not just aircraft development, but the creation of entirely new technologies that will have applications beyond military aviation. The economic benefits of these technological spillovers could be substantial, potentially offsetting much of the program cost. Congressional leaders have privately acknowledged the strategic importance of the program while expressing concern about its fiscal impact. The solution appears to be a funding approach that spans multiple budget categories, making the true cost difficult to isolate in public budget documents. The per-unit cost of the aircraft when a production eventually begins would likely exceed $500 million. substantially more than the approximately $300 million price tag of the 6th-generation F-47. However, the operational capabilities would represent a value multiple times greater than current platforms. How would the 7th-generation fighter change warfare? Military strategists are already developing new concepts of operation that would leverage its unique capabilities. The aircraft's combination of speed, stealth, and space operations would render traditional air defense systems obsolete. No current or planned system could effectively engage an aircraft with this performance profile. In a conflict with a near-peer adversary, the fighter could strike critical targets anywhere within enemy territory without warning, disrupting command and control networks and destroying key infrastructure before an adversary could respond. Its space operations capability would allow it to neutralize enemy satellites, blinding reconnaissance and communication systems. This would create an information advantage that, when combined with kinetic operations, could be decisive in a major conflict. Perhaps most significantly, the mere existence of such a capability would strengthen deterrence. Potential adversaries, knowing they could not defend against such a system, would be more reluctant to initiate hostilities. Despite its transformative potential, the 7th-generation fighter program faces significant challenges that could delay or limit its development. The technical hurdles are formidable. Hypersonic propulsion systems that can operate reliably for extended periods remain elusive. Materials that can withstand the extreme conditions of hypersonic flight and space operations are still in development. The computational requirements for the aircraft's artificial intelligence systems exceed current capabilities. Quantum computing, while advancing rapidly, has yet to reach the maturity needed for the program's most ambitious goals. Political challenges are equally significant. Changes in administration priorities could affect funding. International treaties governing space weapons could constrain certain capabilities. Public concern about autonomous weapon systems might limit AI integration. Yet, despite these challenges, the program continues to move forward, driven by the strategic imperative of maintaining air superiority in an increasingly contested environment. The 7th-generation fighter represents more than just an advanced aircraft. It embodies a fundamental rethinking of what aerial warfare means in the 21st century and beyond. As space becomes an increasingly militarized domain and technological advancement accelerates, the distinction between air power and space power is blurring. The 7th-generation fighter would be the first platform to truly operate across this spectrum, redefining the boundaries of aerial combat. Its development will likely spur similar programs among America's adversaries, potentially triggering a new form of arms race. Yet its technological sophistication would give America a lead measured in decades rather than years. For military planners, the aircraft offers new strategic options that could make conventional conflict less likely by establishing clear technological superiority. In this sense, its greatest contribution might be wars prevented rather than won. What's clear is this: while the F-47 and other 6th-generation platforms represent the cutting edge of current capability, America's defense establishment is already looking far beyond them, to a future where the lines between air, space, and information domains disappear entirely. The 7th-generation fighter stands at the center of this vision. A system designed not just for the wars of tomorrow, but for conflicts decades in the future that we can barely imagine today. If you found this inside look at America's next leap in military aviation technology interesting, please hit the like button and subscribe to our channel for more in-depth coverage of defense technology and strategy. Your support helps us continue bringing you this exclusive content. What capabilities do you think are most important for America's future fighter jets? Let us know in the comments below.